Hello everyone and welcome to today's webinar. My name is Nilu Parvinashtiani and I'll be helping with facilitating today's webinar. This webinar is titled Tools for Evaluating Performance Data for Transportation Systems Management and Operations Strategy and is sponsored by the Federal Highway Administration and hosted by the National Operations Center of Excellence, or NOCO. So as a quick reminder, if you don't know about NOCO already, we offer resources to support the transportation systems management and operations community. So on the top right side of your screen right now, you see a box that is called Useful Links box. You can browse through a NOCO website, previous NOCO recording, and case study resources on NOCO website. You can also be in contact with us and be informed of the latest news on TISMO through our newsletter or just by connecting to us on Twitter. You can also download the PDF of today's presentation from the download pod that you see below the Useful Links box. So just a few logistics for today's webinar. We are recording this webinar, and that recording along with the presentation slides will be available through the on-demand learning section of NOCO website. All attendee phones are on listen-only mode by default, but we do like to have you engage throughout the webinar by putting any questions or comments in our question discussion pod that you see on the screen. At the end of the webinar, we will hold a question and answer session, and the moderator will read each of the questions out loud, and the questions will be answered by the presenters. So throughout the webinar, as the questions come to your mind, please don't hesitate to put it in that question discussion pod. So that's all I had, and with that, I'll hand it over to our moderator, Daniel Grate, to start us off. Daniel.
Thank you, Nilu. Good afternoon, everyone. I'd like to welcome you to today's webinar, which is entitled Tools for Evaluating Performance Data for TISMO Strategies. I want to introduce myself as well. My name is Daniel Grate. I'm with the Federal Highway Administration's Resource Center, and I'm on the Operations Technical Service Team based out of Atlanta. Just to give you some background and motivation for how did we get here, a few years back, you guys may remember the Sharp 2 reliability effort that was underway. Federal Highway conducted about 40 to 50 self-assessment workshops using the capability maturity model. As a part of that assessment, we looked at 6 significant dimensions in which we did a SWOT analysis. One of those dimensions was the performance measures and management dimension. And what we found throughout the assessment is that a lot of agencies are what we call data rich. There's a tremendous amount of data that has been collected over the years. However, there's been very little done with it in terms of using it to evaluate the performance of the system in a manner in which you could use it for decision support for decision making as it pertains to investing in TISMO. So a big part of that problem was that there wasn't a whole lot of tools or best practices out there that could handle big data as it pertains to transportation performance. Since then, we've made some strides, and there are some tools out there, some in the developmental and prototype phase, but there are tools that are available to help with accommodating and analyzing transportation big data. We have 2 of those tools that we're going to be presenting today. The first tool is the Titan tool out of the University of Missouri in Columbia, and the second is a tool, TRIP, by the name of TRIP, that is under development and R&D within Federal Highway. So we're going to go ahead and get into the first presentation, which will be conducted by Dr. Adu-Gyamfi. He is an assistant professor in the Civil and Environmental Engineering Department at the University of Missouri, Columbia. He received his master's and doctoral degree in civil engineering from the University of Delaware and is considered a global resource in big data analytics and visualization. So with that, I'm going to turn it over to Dr. Gyamfi.
Thank you very much, Daniel. And thank you for joining. I'll be talking about Titan today. Titan was developed for Missouri Department of Transportation. Just like most DOTs, as Daniel said, they are usually data rich. You have a lot of data. The problem is how, as the data gets really huge, how to get extract information from the data quickly. So we came up with Titan as a way of, as a platform that can help them store their data and also be able to analyze and visualize it pretty quickly. So that's pretty much what Titan does. So in this presentation, what I'm going to do is I'll first of all give a motivation for this. Why did we get here? How did we get here as transportation engineers? And then I'll go through some of the big data challenges that most agencies face. And then I will look at the Titan platform, the architecture. Just a very high-level architecture, and not go too much into the details of how it was built. But pretty much, what are the components? What are we using to actually build it? And then I will also highlight the solution. What is Titan doing? And how can you use Titan to help you tame your big data set? And then we will go through a demo, an online demo of Titan. So how did we get here? So we always build. And when we build, we want to know how many vehicles are used in our roads. And so we put, for instance, sensors. Put sensors on the ground. It could be magnetic sensors, radar, just to be able to count the number of vehicles that are passing the road. So this is straightforward. If you have a system like this, where you have sensors on the ground or by the roadside helping you to count, it's easy to just build a pipeline to download this data set, process it, and analyze it or visualize it. For instance, on your right side, you have a detector map or in St. Louis. There are, I think, about 1,000 of them. We can easily download data from these detectors and process them and visualize them quickly with any ordinary computer. You don't need any sophisticated architecture to process data coming out of your detectors because the size of data is really small. You pretty much having speed, volume, occupancy data coming out, let's say every minute. So that's easy to process. Any commodity data now you can use it to process that data. But there are cases where it gets a little bit, the limitations of detectors comes to bear. For instance, and I'd like to share my screen here. If you have, let's say, let me share my screen on this one. So we're going to look at, so if you see that video playing, there's a crash that's happening on the freeway, and yet traffic is normal. It's moving, it's not impeded. If you have detectors on this road, there is absolutely no way you will figure out that a crash happened on this road. So that's one limitation of these sensors. Now, to be able to go beyond this, what we did was, I'm going to stop sharing. So what you could do is, okay, why not add cameras? Okay, if I have eyes on the road and I have my detectors, I should be able to monitor my roads. Okay, so in cases like this where the crash doesn't affect the normal flow of traffic, your CCTV cameras could be of help. Okay, now how do you process this data? Assuming you don't process your camera data live, but then you want to process your detector data, you can still use your data pipeline to process these two data sets. Okay, so you're streaming your video data, so you're just streaming it, so you're watching it. And then your detector data, you have some program that is downloading the data, and then you're visualizing and looking at what is going on the road. That's straightforward. You still can use any computer to work with this. You don't need any sophisticated architecture for that. Okay, so we have detector data. We have cameras on the ground. Now, until recently, they need to know travel times, how long it will take you to move from one place to the other. Also brought a new challenge. Okay, if you have detector data, it's really difficult to compute travel time from one point to the other, mainly because your detectors are not covering the whole state, and it's really not practical to do that. Your cameras are also not covering the whole state. So if you really need to compute travel times throughout the state, you need something, data that has much wider coverage. Okay, so we brought on probe data, cell phone probe data. Everybody's using a cell phone. We're all driving, so we can get travel times from these cell phones. Now that has increased the complexity of data processing. Okay, so what happens is now you have probe data, you have sensor data, you have cameras. You cannot do away with your sensors or your detectors because that's what gives you the counts, the volumes. Probe data will not give you the counts, but probe data will give you travel times. You have cameras which will help you to see what's going on the road. So you can't really throw any of these data sources away. So we still have to use all these data sets. Now that's what creates a problem, because what is happening is now you have multiple data sets that you need to use to make decisions. Okay. I have access to some Missouri data, and if you look at, I have access to about 1,500 cameras. I have access to probe data, which every day increases about 25 gigabytes. So you have 25 gigabytes of probe data for the whole of Missouri every day. You have about 2 gigabytes coming from the census alone. And you have 1,500 cameras. Now, if you put all this together, that's a lot of data to process in a day. Okay. Your pipeline for downloading data and analyzing data and visualizing data completely breaks down when you get to this limit. Because if, for instance, if you need to analyze data for a week, probe data and your sensor data alone is going over 100 gigabytes. So it's really going to take a lot out of your computer to process those data sets, less of all visualize it. So this pipeline is not going to work. We need a new architecture to be able to download our data, process it, analyze it, and communicate or visualize it. And we get into what we usually call the big data problem at this point. Some of the challenges that comes with this is, first of all, how do you store the data? You're getting about 30 gigabytes a day. How are you going to store it? It's really cheap to store data nowadays on the cloud. You can easily do like $5 for a month for a terabyte of data on AWS. That's really cheap. But because the data is huge, over time, it's going to catch up to you. It's going to get so huge, even after a year, you get into terabytes, and it's really, really difficult to store it. The data is also not structured. So you have video, you have tabular data, you have text data, images. Because it's not structured, you just can't take them and dump them on a hard drive. You have to find an efficient way to store these data sets. Okay, so storage is a problem for big data. The next problem is integration. So because the data sets are huge, when you integrate them, they get exponentially huge. Okay. Now we need to integrate data sets, of course, because we want to answer really new questions, very important questions. One of the biggest challenges with integration is the fact that these data sets are vendor-driven. So you get one vendor to give you your probe data. You get a different vendor to give you your crash data. These two vendors don't talk to each other. So you don't have a unique ID to link these two data sets. Worth of data is also huge. So data integration is really important, and we have to be thinking of these if we are thinking of being able to answer really important questions about our systems. Now, for instance, if I take probe data and merge it up with my crash data, there's so much I can do with that information. For instance, I could understand how the crashes in the state are affecting traffic flow. Because my probe data is telling me about my travel times, the crash data is telling me, hey, there's a crash here. If you know the travel times before and after the crash, you will be able to estimate the cost of the crash. If you have your probe data merged with your cameras, you can explain why certain segments are getting congested. So you see high travel times on a segment, you pull the camera that's closer to it, you should be able to explain why. Maybe there's a crash, or maybe something happened, there's a stranded vehicle on the side of the road. Merging these two data sets will help answer new questions. Or you could actually add your weather data also to it and answer way more questions about your system. Okay, how you can get the impact of weather on traffic flow. You could also, if you merge your signal data with your probe data, you can separate controlled delays from uncontrolled delays. Without merging these data sets, you can't answer most of these questions. Okay. So the need for integration is key. But as we do integration, we have to realize the data sets are huge, and so integrating it, you need a new way of thinking when you're trying to integrate these data sets. You need a platform that can help you deal with big data before you can do this. Another challenge with big data is how you visualize the data. If you have a very small data set, it's easy to visualize on a map. If you have a huge data set, it is very difficult to just use the browser to do that. And sometimes you don't want things to be really slow because people lose interest once your visualization is just really slow. So most of it, how we've gone around this is we have reduced the data. So we reduced that data set, and then we visualize an average or a very small sample of the data set. But sometimes that has limitations. You're not able to see the true trends. So big data visualization is one big problem that needs to be solved. So we could be looking at different ways of visualizing our data. Now, most importantly is interactive visual analytics. What I mean by this is you're not just visualizing the data, but you're also doing computations as you visualize. So you zoom in into a particular county. You want to be able to see what are the average travel times in that county. How is the travel time changing over time? What is the planning time index here? So you have different things you're computing as you visualize it. And you want it to be in real time. You don't want it to be very slow. Because the data is big, to be able to interact and visualize and analyze the data, you need a platform that can handle big data. So this is how we came by Titan. We wanted a platform, first of all, that is open source. So we didn't want to invest into already proprietary software. The reason is there are just too many things. You can get one proprietary software and it doesn't fit what you need. So our goal was go out there, this is what we need, try to get all these open source platforms, write a program yourself, recode it, and try to use it to solve the problems that we need. So everything on Titan is open source. Every program we have is open source. Titan provides a visualization dashboard. It helps you to integrate, visualize, and analyze data on the browser. Okay, so this is not done on any, you don't have to do this as a software. This is in the browser. You go to the URL, you have your data there, you can analyze it, visualize it in the browser. It also has a data center, so it hosts all the data sets, and you can upload or query data sets from Titan. And we use our tools to help you upload data quickly and query data quickly also. And it also has a predictive analytics part, which is it uses machine learning to do analysis of the data that we have. For this presentation, I'll mostly focus on our dashboards, which helps you to look at your performance data, query data, and visualize it. So I'll briefly go through the architecture. So what we're doing is, first off, we have a variety of data sources. So currently we have AVL data that's from bus fleets, mainly in St. Louis and Kansas City. And we have your CCTV data, we have probe data, signal and detected data, and crash data, and some historical databases. So what we do is, Titan has, we call it a data ingestion engine. It basically connects to these different sources of data and pulls data simultaneously from these sources. Now, when we pull those data, we put them on the cloud. Okay, we store them on the cloud. Now, because these data sets increase exponentially with time, you just don't want to take the data and dump them on a server on the cloud. If you do that, when you have to go back and pick up the data, you will have issues. It's just like think of it like if you have a CSV file. If the CSV file is 2 megabytes, it's easy to open. If it's, let's say, 200 megabytes, it's a little bit more difficult to open. Okay. So as the data increases, you want to store it efficiently such that when you go back to retrieve your data, it doesn't take too much time. So what we do is we build a cluster on the cloud. Now think of a cluster as a bunch of computers joined together. Okay. So instead of using just one computer to process and store our data, we have a bunch of computers networked together. And so if we have, let's say we have 100 gigabytes of data that we want to store, we just don't store it on one computer. We break it into chunks and we split it across our servers. So each computer is storing just a small fraction of the data that we have. So for 100 gigabytes, if we have 10 computers, we can break it into chunks of 10 gigabytes and store them on each of the computers. Now the beauty of this is, now each computer only has, if you have 100 gigabytes, and each computer is only dealing with 10 gigabytes. Okay. So it's much faster to upload and it's much faster to download because the computers are not all working on 100 gigabyte file. Okay. Now there are open source tools out there to manage clusters. Hadoop is one of them. Spark is another. We use both of them on Titan right now, and it helps us to manage our clusters very well. Now on top of our cluster, we also have some databases that helps us to query information quickly. We have what typically people call the NoSQL database. The NoSQL databases are used when you have data sets that are not structured. So for instance, I want to store a video and my travel time and my crash data in the same place. If you want one database to store these, because they are not in the same format, so your crash database is like a table, CSV, your video is just a bunch of images. You can't fit all these into one table. So NoSQL database helps you to store such more unstructured data sets. And we also have GPU databases and other programming applications like Spark. Now, GPU databases are really important if you need to do computations. So when we really need to do very fast computations on big data sets, the GPU helps us. And GPU is a graphic processing unit. It uses the graphic card in your computer. That's pretty much what it is to do our computations. So this is pretty much how our backend, our cloud looks like. It has a distributed cluster, and it has all these databases sitting on top of it that helps us to do quick querying and analysis. And because of how it's structured, we are able to store different types of data, process different types of data, shape files, video, images, and all types of structured tables. Now, once you have your database structured, what Titan does is it runs what we call the integration and correlation. So it integrates the data. So it'll take my probe data and the crash data and CCTV cameras and integrate it. So when you pull up a crash, you should be able to know what the travel time was and what's the closest camera. So all these things are integrated. So we don't have the data sets. Our data sets are not sitting by themselves. They are integrated. So your weather stations will have, if you pull up a weather station, you will know what crashes happened closest to it, what are the sensors there, what is the probe set data there. So, and we usually use spatial and temporal conflation to do this. And most of this are automated. The integration is automated, and then after it's automated, we get students to kind of manually check if the conflation is correct or not. So you have your database. You've integrated all the data set sources you have. Next is build applications on top of it. So all the different applications you can think of. We have the place to query data. You have your dashboard center. You have areas where you can do your performance measurement or your predictive analytics. Because the data is integrated, all these apps can be deployed. And we are using big data software in the back end. So things are really fast. So if you want to visualize something, if you want to query something, it's very, very fast, irrespective of how big the data is. Okay, so that's pretty much the App Center. It has all these dashboards that helps you to interact with the data that you have quickly. And here, most often, you don't really even have to download data. You don't have to take any data out of Titan. Everything is done here. So your data is there. Your analysis can be done there. So you're not having to pull data away. All the analysis is also there and on the same platform, which helps a lot, especially if you're dealing with very large data sets. Okay, so at this point, I would want to do a demo. So we have a website out for Titan, https mizzutitan.com. And I would want to do a demo right now and take a look at some of the applications we have out there. If I can get a share screen, that would be great. Good. Okay, so I think once you go into Titan, you should see this page. We have interactive dashboard, data center, and then you'll have the predictive analytics also there. Now, this is mobility, so I can look at, so the mobility section just takes a look at your probe data. So this is just one data source. Here I've loaded in 1 year of probe data for the state of Missouri. Okay. That's close to about 100 gigabytes of data. Now, as you can tell, this map is visualizing. This is pretty much your travel times along the road segments for a whole year. Okay, so you can zoom in and out. There is no lag. There's no latency. Pretty fast. Now that's not just that. We also want to do computations. Okay, so if you look down here, if you go down here, we have charts that are going to tell you, show the analytics part, the computations. So you can select whatever you're interested in. So for instance, if I just want to look at freeways in the state of Missouri, I think this should help me with this freeways. And immediately all the charts get updated. Okay, so these are doing calculations. If I could explain these charts a little bit. So the first chart here, that's my travel times, how long it takes you to travel 10 miles on all freeways. That's the average on all freeways in the state. Okay, this line chart here is your hourly travel time. That's my planned travel time index. If I go down, you can see the top counties that have the worst travel times. Of course, St. Louis will be there, and Clay, Jackson, and Kansas City. And this one is telling you which road segment is actually having the worst travel times. And that's pretty much the percentage of hours congested. And there is also a table here which will give you the details of travel time for that particular, for those freeways. So I can pretty much check it out again, and everything else gets updated. Now, when it comes to your line chart, you can actually filter what time you want. Okay. Now, as you move it, as you can tell, the graph gets updated. Now, we are looking through almost 100 gigabytes of data in the browser, and it's not even blinking. It's pretty fast. It's because of the architecture we have in the backend. Okay. Now, with the map, you can actually interact with the map also. So I can just take a look at what is going on just here in St. Louis. Because the map is a little bit, you have too many points on the map. That usually will take a few seconds. But here we are, we have everything that's going on in the area I demarcated. I can move this around. I can move that to another location, and it will update my parameters for that. And you can look into what is going on in this area. You can look at what county, what specific county you're looking at, and move these around. It's just being able to analyze your data quickly without having to spend much time downloading data, trying to compute certain measures. Everything is done here in the browser for you quickly. We can also look at, let me use our integrated one. So the safety and mobility is pretty much integrating your probe data with your crash data. Okay, so we have crash data, and then we have probe data, and integrated that with the weather data. And so here you have the map showing you the size of, I think the size of the bubble tells you how many people were killed. And the color is pretty much, I think, that's how many vehicles were involved. Down here, you have congestion. So this is estimated from the probe data. So this is congestion in minutes for all the crashes that happened. Now, if you look at this, of course, if you look at the crash types, rear-end crashes are usually most. Especially as you zoom into the St. Louis area, because of course it gets congested. You have a lot of the presence of queues around the city, so your rear end will go up. Now, if we try to go away from the city, look at how our crash types changes. Let's see. So we're going to move out of the city. A little bit out of control vehicles take control. It tops the rear end collisions, crashes. And you can tell that your congestion level actually drops so much in those areas. So rear end, you don't see much rear end crashes outside cities. What you usually see is the out of control crashes. We could also look at, let me zoom this out, and feel free to go to the website and play with this. We can look at fatal crashes. Of course, most rear-end crashes are not fatal. So you see out-of-control crashes are mostly fatal. And you can look at the weather condition when these crashes happened. These are the weather conditions when it happened. Now, I am looking at 4 years of data here. This is 4 years of data, crash data, integrated with my probe data. And I'm analyzing it without any latency. Okay. That is really difficult to do without a platform like this. You will see a lot of latency. If you try to do this with any other programs like Tableau or Power BI, you will see a lot of latency if you integrate that much data. But coming up with this architecture, it enables us to sift through this data without spending so much time. Okay. We can go out of my share screen. Feel free to take a look at it when you have time. And this is pretty much something I was saying in the last. We also have capabilities to look at video, to analyze the video. We have our machine learning systems that can connect to cameras, and it will tag the cameras, whether it's congested, whether there's snow on it, free flow. It can also count the vehicles that are passing on a section. And what we do is we put it in the database. Our goal is to use this to help the TMC. This particular framework is to use this to help the TMC. So instead of looking through a bunch of cameras, trying to figure out where there is a stranded vehicle or not, or whether it's congested or not, this system pretty much does that for you. And I'll want to share my screen again here. So if you look on my screen up here, this is the system we have. You can pretty much search for different conditions on your camera. So here I'm typing congested, and it's going to pull up every camera that's congested for you. So you can type in so many things. So you can type snow, you can type stranded vehicles, type in stranded vehicles, and all that, it will pull up those for you. So that's one application that we're using Titan for when it comes to looking at video analytics. This is still in progress. We are also actually working with some MPOs and counties to get more data into Titan. So we want to extend this to bridges, pavements, geotechnical assets and all that, and pull data from that. Because most of these data sources can also be integrated with traffic data. And it will be very useful to have all these in the Titan platform. We are building more predictive analytics tools based on this, because we have the architecture, we have the infrastructure to run our machine learning models already. So all you need is pretty much having the data that you can use to train your models and come up with those predictions. Just one thing I wanted to talk about. So whenever you're trying to implement something like this, there are four big things. You want to think about cost. Now, if you want, and I think most agencies want, I think it's changing, but it used to be that most people want to build things in-house just because they wanted to have the control and security, be able to secure their data. You can pretty much pick Titan up and then make it an in-house thing. That's totally fine. Right now it's running on Azure cloud. It's pretty much costing us close to about $1,500 a month, which I think for a system that's complicated, I feel like it's worth it. The only thing is, if you do this in-house, you have to think about administration. Okay, service goes up and down almost within every month. So you need to have someone who is dedicated to this. If you do it on the cloud, you don't have to do that. Security is sometimes an issue on the cloud, but there is a way around it most often, and especially when the data is not private information. You're not seeing people's faces and all that. Security is really not a big issue. And then when it's on the cloud, it's very flexible. You're very flexible. You can really tear down things and put things up easily. And now the price of cloud machines are really going down. I will say going to the cloud is a much flexible and easier approach to do this. But you can also pull this up in-house. So in summary, this is pretty much what Titan is doing. It's providing you with an efficient way to store and retrieve large data sets. It will help you integrate different data sets, link them up, and then you can actually interact with it. You can visualize data, you can analyze the data using our backend. So that's pretty much what Titan offers. Feel free to explore the website that we have We are probably going to revamp it very soon, but feel free to explore it. And if you have some data sets you would want us to also test using it, you're welcome to share it with us. Thank you.
Okay, thanks, Dr. Gyamfi. Next up, we have the TRIP tool, which stands for Transportation Research Informatics Platform. And James Pohl, the Director of Safety Research and Development at Turner Fairbanks, will be providing this presentation. As that's being pulled up, I want to remind folks that if you have a question, please put those questions in the chat pod, and once the presentations are done, we will go through that chat pod and conduct our Q&A session. Thank you. James, thanks.
Certainly. Thank you, Daniel. Thank you also to the National Operations Center of Excellence for inviting me to participate today. And also, I want to thank Dr. Adu-Gyamfi for the presentation about Titan. That was a fascinating view of a tool that was developed there. What I'm going to be talking about regarding TRIP is fairly similar in scope. There are some distinctions in between TRIP and Titan, but I think that the demonstration of these two different tools represents a kind of an emerging mindset, both in the fields of safety and operations, of being able to leverage a wide range of data sets in order to come up with actionable solutions to address the range of challenges that we're confronted with. So a little bit about TRIP, and again, this is a little bit of retreading of what Dr. Adu-Gyamfi had described before. A lot of agencies are working with unprecedented amounts of data. And so what was intended with TRIP is to have an end-to-end informatics-based solution in order to be able to meld these different sources of data to make them actionable. The focus when we started on the research project for developing TRIP was focusing on open source tools as much as possible, partly because of costs and also partly because of the efficiency, scalability, and customization that could be enabled through open source tools. Also the tech transfer of these tools, because the intent here is to create ultimately a tool that can be shared and used by state DOTs, local partner agencies, at the municipal, local, and state level. And even though I'm the technical director of safety research and development and federal highways, the focus of this is not strictly on safety analyses. This can support a range of planning, operations, even policy analysis. It really depends on the time scale of the data that you're looking to work with, and addressing the spatial and temporal resolutions of the data that you do have to work with. So in the scope of the research project, and those are really very high-level prototype diagram for how TRIP was constructed, the idea that we had going into this was focusing on the items that you see indicated on the upper left in red, HSIS, which is the Highway Safety Information System, which is a data resource that we manage in the Office of Safety Research and Development for purposes of long-term longitudinal tracking of crash trends, because roadway design changes over time, vehicles themselves change over time. And so how vehicle and roadway interactions manifest into crash types is something that we observe over time as developing trends. Claris was a research project that I helped launch back in the early 2000s, and that was intended to aggregate roadway information system data from a number of participating states. I think at one point we had 35 participating states, as well as 6 Canadian provinces contributing into for what was at one time the largest largest mesonet in North America. And then also working with part of the Sharp 2 project. Under the Sharp 2 safety program, we have the naturalistic driving safety data, and there's a complement to that called the roadway information database, which has information on the traffic characteristics, crash information, as well as the roadway geometry characteristics from right-of-way edge to right-of-way edge. So you really have a very full composite just from those three different types of data sources. But what we envisioned going in was that there would be an expansion of other types of sources from basic safety messages from connected vehicles, for instance, being able to bring in cell phone data, anonymized cell phone data from different aggregators that exist out there. And then also related transportation data, things such as social media. And that there have been a number of different analyses that have been performed over time about using Twitter messages, for instance, to be able to extract information that could be of transportation use. The idea of this was to bring this all together into a common informatics platform that would enable novel transportation research. And again, this was a research project that I'm describing here. What we did in terms of the research project was really go through a proof of concept test or demonstration. And what we did in terms of using informatics to come up with analytics was being able to develop some predictive analytics. And in this particular instance, we were looking at the feasibility of being able to predict crashes within a time span ahead of present time. So T plus 15 minutes or T plus 30 minutes, what would be the types of crashes that could occur. And then also developing some advanced visualization, similar to what Dr. Adu-Gyamfi had described in Titan. In working with in the creation of TRIP, the idea here, again, is focusing on open source tools and also trying to apply some level of artificial intelligence in order to be able to come up with ways of being able to package the data, aggregate the data, and find commonalities among different data sources. So that way, one who has some complex analytics query would be able to comb through effectively the disparate sources of data that could be attached to TRIP. TRIP, to reiterate, is not specific to any particular domain. You just need to be able to attach sources of data that may have some degree of commonality. Some of that could be spatial, some of that could be temporal, some of that could be subject matter also. So depending on the complexity of the query or the complexity of the analysis that you may be working with, the intent of TRIP is to be able to look across the different types of data stores. So similar to the architecture for Titan that you heard described a little bit earlier, there's a system of being able to capture the data, be able to ingest, manage, and transform the data, be able to process the queries, and then also be able to present either the input in order to construct a query in a meaningful way, and then also to be able to receive a visualization or some kind of output. So those are the three broad areas of client applications, data services, and back-end systems that I described. A little bit more of a deeper dive into the research project or the scope that we had for TRIP. What we had was through a web client of some sort, we would have a REST request, and REST just stands for representational state transfer, and it's an architectural style that helps streamline being able to extract types of queries from other types of data processors. And in this particular instance, they were basically requests for JSON types of results. So JSON is JavaScript object notification. It's a way of being able to package data so that way could be uniformly carried over to a viewer of types. And of course, in working with just those three different data sources of Highway Safety Information System, Roadway Information Database, and also Claris, you're dealing with a lot of different data. There are geospatial data. There are different types of data for in different temporal resolutions and spatial resolutions. And then the data were collected differently. So Highway Safety Information System has a lot of crash information. So does the Roadway Information Database. But the Roadway Information Database was constructed with crash information produced by the participating states that participated in the SHARC-2 data collection. So there were some anomalies that would occur naturally as you work with different entities and their different sources of data in order to be able to come up with a composite. Over on the right end of the spectrum, there's analytics in terms of being able to look at the spatial distance, weather proximity in terms of different types of events, and this is partly related to Claris, dealing with aggregation, machine learning models, correlation, interpolation, and entity resolution. And I'm going to elaborate a little bit further on those two red items. But in the context of the research project that we did for developing TRIP, just with those three different sources of data, Highway Safety Information System, Roadway Information Database, and Claris, we had 88 tables containing a total of 60 million records and 9 billion cell values. And then completely uncompressed, just looking at them in their raw nature, it amounted to a little bit over 10.15 gigabytes of data. After ingestion into TRIP and applying some of the tools that were TRIP itself being a composite of different open source tools, able to compress that down to about 5.03 gigabytes of data. So it becomes more manageable and a lot quicker to be able to produce some kind of analytics results, depending on, again, the type of query that someone may be considering. And I lost my cursor for a moment there. And so what I mentioned before in terms of the types of analytics, and I touched upon machine learning and entity resolution. I'm just going to give an illustration of these. So for a machine learning model research question example, a question may be, what roadway curvature characteristics present an increased risk factor for commercial vehicles? So the source of data for this particular instance happened to be RID. And again, that was something that was facilitated working through the TRIP platform to identify what would be the most ready source of data. And then it just kind of goes through the different types of analytics, in this particular instance, stack box plots, and also the machine learning model. And then going through the different steps of the analytics itself, things such as retrieve a set of crashes that have curvature, attempt to model the crashes using curvature characteristics as a source of information, and then select different types of machine learning model types as the basis for evaluation and report the performance of those models. And so what ultimately results in terms of an output is a combination of roadway curvature characteristics and event-based crash data that can provide many different opportunities to gain insights using a variety of different analytics, visualization, and training techniques. 3 different models were invoked to return results for this particular question. They include a decision tree, a random forest, and a k-nearest neighbor model. And that last sentence refers to a couple of different, or several different machine learning models that were used for being able to explore the data itself and come up with some meaningful output. Ultimately, the analyst, as she works through TRIP to be able to come up with these complex queries, would have to make a determination about what was most suitable to suit her purposes. And of course, I mean, this doesn't exclude the value of the analyst herself in terms of being able to come up with some kind of meaningful analysis as a result of working through a tool like this. Entity resolution is somewhat related, but interesting in its own right. So for this particular instance, a query question or a research question may be: find all senior drivers who struck pedestrians at intersections with crosswalks, but without pedestrian crossing lights during twilight hours. So this is an entity resolution problem where TRIP would look across a couple of different data sources at the same time, in particular, Highway Safety Information System and the Roadway Information Database. And then using the analytical method of entity resolution, it would actually look at a sample of drivers with an age greater than 40, and then attempt looking at joining criteria for date of events, age of driver, gender of driver, vehicle year, vehicle make, et cetera, et cetera. And then it would produce a set of results of different crashes that met the criteria in Highway Safety Information Systems, and then also the same types of crashes that occurred in the Roadway Information Database. Again, as I mentioned before, Highway Safety Information System and Roadway Information Database, although they are describing largely the same thing, were produced by two separate entities. And so over time, there just become data distortions, especially as you work with data from that originate from different sources. So here I have a more graphical representation of what that entity resolution was for that particular question. So what TRIP does is it automates some of the data discovery, looking across both Roadway Information Database and Highway Safety Information System. It looks at what were the potential cases that addressed the question about elderly drivers striking pedestrians in locations, in crosswalks where there was no lighting available. And so it looks across all of these different records, and it develops a score, kind of like a goodness of fit, so to speak, in which there are effective matches in terms of roadway type. Is it a tangent or a curve? What was the condition of the roadway surface? And so as best as it can, what it does is it helps the analyst to determine what are useful records that she may be able to work with to explore the question. So on the left-hand side, where you see the score that says 11, so there's a lot of similarities among the fields and the records. So this would probably be a good set of matching records that help a lot. And then in the middle where you have a -3, well, that's probably where the analyst would probably do a little bit more handiwork. There may be some coding errors, but ultimately she may make a judgment of determining, well, maybe this is going to be suitable, so I'll go ahead and work with this. And then on the far right, where the score shows a -11, this shows that there's a lot of disparity between the two different records. For what was cast as a like event has completely different types of vehicles. One has a female driver that's 19, another has a male driver that's 56. And so the commonalities really just start disassociating there. And so that's probably one where the analyst can leave that out of the scope of her analysis and concentrate on the other two different types, so that way she can go ahead and proceed. The idea behind all of this is to help reduce the data discovery time that an analyst takes in order to be able to conduct the analysis. Approximately 80% of all complex data analysis involves the data discovery itself. And the intent here is to be able to flip the script on that and make the data discovery a much smaller proportion over the total time for analyses. So that way the analyst can actually come up with some meaningful and effective solution to address the question at hand. So in terms of constructing this, there's a query builder, and again developed in part of working through Kubrick, which we had contracted with. The tool itself uses a visual query builder in which one is able to literally graphically design a query and see some of the particular results that could be generated. So in this particular example, there's a question related to looking at within a date range, looking within a geographic range, and then filtering by fields in this particular alcohol test, because part of the naturalistic driving study data included information, had alcohol sensors in the vehicles themselves. And so we did actually record information or records of trips in which there was presence of alcohol detected. It doesn't necessarily mean that there were drunk drivers that we were recording. It just simply means that the presence of alcohol happened to be there. So, it's, what you see here is a histogram that shows in terms of a particular date range and the number of different types of crash events that have occurred within the date range. And then it's possible for one to go ahead and filter down further and see what proportion of that histogram actually relates to presence of alcohol. And the user interface itself, again, is very highly graphical and allows one to do some simple visualization, and then working with a query builder, be able to build up very complex analyses or queries to extract data that demonstrate a range of different items. Where we did, for purposes of this proof of concept research work, we focused upon the data sets available to us from the Seattle metropolitan area, where we had a lot of detailed information from King, Pierce, and Snohomish counties. It was one of the sites for the Shark 2 safety data, so we had access to highway safety information system data, roadway information database, and then also Claris, all available. So that seemed to be a suitable site for demonstrating the proof of concept of this. It's possible to establish, again, simple temporal queries. In this particular instance, this is looking at the month of November 2012 and being able to extract from that all the different crashes that occurred and geolocate all the crashes that were available through both HSIS and through the roadway information database. The crash attributes are available when one clicks on any of these buttons. And so one would be able to identify that the source was from, the data source was from the roadway information database, information about the driver. This was a 21-year-old in a crash. So it's possible to be able to look at some general information about where the crashes happen to be located. And it's also possible to do spatial queries. Again, this is concentrating around the Seahawks Stadium in Seattle and looking at the November 2012 timeframe. Whoops, I went a little too far. And so it identified the particular types of crashes that were immediately around the CenturyLink field. So that's represented in these blue dots that one may see immediately next to the stadium, and then along Interstate 5 and a little bit further off. As I mentioned before, there are a number of different data sources that one can examine. This has that capability. So this is a histogram distribution for ALT attribute, and that would be alcohol test result. As I mentioned before, in SHARP2 data, there was an alcohol presence sensor, and so it's possible to be able to identify the amount of alcohol presence detected, as well as the amount, the total amount that was where that was recorded within a specified time period. Mentioned also Claris as a roadway weather information system source. That kind of data was also included. So what you see there in green are locations that were Claris stations. Those are roadway information systems which had data that contributed to the Claris system, and then crash location. So it would be possible to, at least within some limited geographic scope, be able to understand what some of the pavement conditions may be that could have been a contributing factor. So for this instance, it would be sensor readings for participation intensity. And again, one would be able to look at time of event and determine whether or not there may have been presence of precipitation that could have caused a loss of friction. It's also possible to, within TRIP, we ingested data from NextRad. So it's, again, this is a span of the crashes for November 2012, but it's also possible to pick a day and observe what the weather patterns happen to be in terms of what precipitation could be occurred on a given day, and even hour by hour, and just look at what the impacts of that may have been on crash manifestation. And then also there's dashboarding that's enabled through this. What you see across the top is a breakdown of crashes that are property damage only, injury, and serious injury. There were no fatalities that were recorded in the scope of the SHARP2 data collection period, but of course, being that some of the data came from Highway Safety Information System, as well as Roadway Information Database, there were some fatal crashes that were noted in that. But this is a histogram that shows day by day over the span of November and December where the crashes happen to be located, and whether in Snohomish or Pierce or King County, and also projecting the level of severity. There's also information that one could dashboard almost anything, but looking at the rural accidents that occurred day by day and seeing when there happen to be trends for more rural types of accidents, the collisions involving people, collisions not involving people, and then just a range of urban accidents. Again, looking at what kind of facility where the crashes occurred and seeing what the impact of that may have been. It's possible also to ingest and output real-time operations feeds. The screen thumbnails that you see on the right are live, well, not on this particular instance, but what were possible to do was to be able to produce live video feeds from a number of different cameras that Washington State DOT maintains throughout the Seattle region, as well as having ATR counts for which would normally be input for HPMS reporting, highway performance monitoring systems. So it is possible to ingest a range of data that are both archived as well as real time and be able to make something actionable out of that. So we developed this, and we're continuing to work with TRIP and Federal Highways. And part of the reason why is that there's no current commercial off-the-shelf system that can integrate disparate and unstructured data in a way that provides value for transportation researchers and practitioners. So the value of TRIP is that it doesn't matter whether or not the data are structured, semi-structured, or unstructured. It's able to accept it all in a scalable way, ingest and align and store the data, and then be able to establish linkages among those different data to make them effective for analysis. And it's highly scalable. It's capable of handling very, very large amounts of data. And again, depending on the scale of the problem that one may be working with, it could be something that could work on a small server system or be configured to 100 machines with no additional configuration. So it's nimble enough and flexible enough to be able to suit the needs of what Federal Highway anticipates to be the needs of many agencies across the country. All state DOTs and local partners are data-driven organizations, and right now most of the data stores, and I've seen this in 25 years of working in intelligent transportation systems myself, is that most data stores are defined to suit a very narrow purpose, a narrow application purpose. And so that's a big challenge in and of itself. So as Daniel Grate had introduced at the start of all of this, a lot of agencies are working with lots and lots of data. They have a lot of data accessible to them, but what information can be made out of all of that data? And it's exciting to see the progress of Titan in Missouri, and I'm aware of others in other pockets around the country where they're trying to explore that issue and come up with effective ways of combating this. However, there's still opportunity for coming up with ways of connecting the dot that we really haven't explored before. And an example of this, what I mean by connecting the dot, that there's a lot of value in other sources of data that could be used for justifying infrastructure investments, for instance, or considering a range that could have impacts on planning that we just haven't had the opportunities to explore, simply because we are working with too much data. So an example of that is, and here's a link to it, is a paper from 2009 from National Bureau of Economic Research, which looked at the introduction of EasyPass and noted that it reduced the prematurity of low birth weight among mothers within 2 kilometers of a toll plaza in the Garden State Parkway in New Jersey, which is a surprising and yet confounding outcome to have from the introduction of electronic toll collection. So what other opportunities are there that we can leverage for improving upon operations or safety or planning or policy that we just haven't been able to experience yet? So that's what we're trying to look for in tools like TRIP to see what can be done to help with nationally scaled transportation performance measures. And so the research objectives that we have is that, by and large, states do not have the technical ability to analyze large data sets, and they typically contract this out. And ultimately what occurs is, or too often what occurs is some shelfware. And what we want to do is be able to get beyond that, where we can come up with tools that can migrate in effectiveness over time, find a large pool of users who can use it consistently, as well as can contribute to making advances. And by contribute, I mean intellectually contribute to making advances to those kinds of tools. For instance, within my office, we're examining the use of TRIP for augmenting the capabilities of highway safety information systems, which currently houses data from 7 states. But we know that there are a number of other states that produce just as good quality of safety information data, that could be ingested and be able to be aligned in a very, very low-cost way. As I mentioned, this is all a research project. The final report is available. We conducted a technology readiness assessment, and this was assigned a technology readiness of the level of 5, which means that the integrated components were demonstrated in a laboratory environment. That's basically saying that as a system and in a controlled manner, this works. And if you're interested in learning more about technology readiness assessment, there's a link there. It's technology readiness is not something new. This is actually created by NASA for determining what projects or what kind of technologies are suitable for being able to launch into space. What we've done is we've repurposed their approach for purposes of developing transportation technologies and understanding when our research is ready for demonstration. In terms of where we are right now, we're in a phase of what's called accelerated market readiness. What we're trying to do is we're launching new activity this year for advancing the technology readiness level 4 trip from a level 5 to a level 8. And level 8 means that it can operate effectively and prove to operate effectively in an operational environment. So in other words, it would have to be able to work with a TMC. It would have to work with a safety office or a planning office or some combination of the two. And what we need to do is to create more use cases in order to demonstrate to end users how the informatics platform can be used for analysis. So that's going to be a lot of the concentrating effort over the next several months, is coming up with effective use cases. And the paradox is that for TRIP to be attractive to state and local agencies for their analyses, these agencies need to see a variety of analyses conducted to demonstrate the effectiveness of the platform. So Federal Highways is going to be working with a segment of the user community external to Federal Highways, working with different state DOTs, MPOs, other local partners, and see about creating some use cases so that way we have a model to work with that could be carried out further to other states and that would be attracted to those. How that might roll out a little bit further downstream, it could take shape over the course of the next year, but certainly we would be very interested in hearing any kind of feedback or interest that you may have in being part of this use case development process. And that's pretty much it. There were in my slides a number of references to different types of tools and technologies. I do have to have an official disclaimer being from the federal government. The U.S. government does not endorse or products or manufacturers, trademarks or manufacturers' names appear in this presentation only because they are considered essential to the objective of the presentation. They are included for informational purposes only and are not intended to reflect a preference, approval, or endorsement of any one product or entity. And with that, thank you.
Thanks, James. So we're going to jump into the Q&A session. We have one question in the chat pod for Dr. Adu-Gyamfi for Titan, and it comes from Angela Catali. And her question is, regarding probe vehicle data, are there any specific sources Titan is receiving data from? Do you receive the data in a raw format and have to process them yourselves, or receive already cleaned up data?
Right. So our probe data comes from a vendor called HERE. So I think there are different vendors, NRIX, HERE, Nokia, and some other vendors. But ours come from HERE. And the data comes to us aggregated 5 minutes for each segment.
Okay. I actually have a question, the same type of question, but for TRIP, in that, James, for the data that's coming out of these different systems, you had HSIS, RID, to name a few, Claris. same type of question. Is the data already cleaned up, or do you have to process it yourself? Does TRIP have some type of AI component that, you know, kind of learns from the information and builds its own clean up process?
So, you know, probably the cleanup process would be the entity resolution, in which TRIP is able to look across records and down to specific fields and see how different records from different sources of data appear to align. So in the example of HSIS and roadway information database, those were two different, even though they were describing effectively the same thing, they were produced by two separate entities completely. And it's interesting how you can have two different organizations look at exactly the same types of events and describe them in a distinct way. And so the challenge is being able to look through that. HSIS is probably a bit more managed because there's a rather intensive data quality control, quality assurance process from all the different crash records that come from the participating states. I mentioned that there were 7 participating states in HSIS. And so you can imagine the police reports from California, Washington State, Michigan, Maine, among a few of the states that participate in TRIP. The crash reports from the police are going to be pretty different, even from within California. You've got police reports from at least 50 different entities. So the process of coming up with QA, QC, and HSIS is a bit more managed. But again, that's the value of the approach that TRIP takes, is that now, if you've got raw data that's a complete mess, it may not be as effective. But the idea here is that the handiwork that one would normally take in terms of doing all that QA, QC at the front end would be something that would be largely automated through something like TRIP.
Okay, thanks, James. Okay, let's see. I actually have a question. In terms of pre-positioning resources, so to speak, for the DOTs, has TRIP or Titan been used for any type of activities as such? For instance, TIM or incident management. With the historical data that you have you been using, has MoDOT or WashDOT been using the information to, look at where particular hotspots may be for AM and PM peak to pre-position, say, service patrols? And in another situation, let's say planned special events, whenever you have a annual planned special event, like a festival or some sort, are these DOTs using the information or analysis to figure out which strategies, TISMO strategies in particular, should be in place to help with travel time reliability? We'll start with you, Dr. Yao.
Yeah, so that's a really good question. So Titan was mainly a research project that we launched. I think the report came out about maybe 6 months ago. But yes, our goal is to be able to use it, for the DOT to use it for travel time reliability and all that. Now, at this point, we do not have the DOT using it because we've just finished it with the research group, and we are still undergoing the advertisement and encouraging people to use it, because right now Titan has the capability to be used for looking at travel time reliability and all that. For pre-positioning service patrols, that's a really good question. That's something that has come up in my discussion with the TMC folks. And currently we're actually working on that, how to be able to use the predictive analysis that we have to pre-position service patrols. It's not currently being offered in Titan, but that's because that requires a little bit more real-time data, which we don't currently have access to. But yes, that's something in discussion.
Okay, thank you.
And my response is similar to Dr. Adu-Gyamfi's. What we have so far is a proof of concept demonstration working with large data sets. But the intent is, again, working with developing some use cases in order to test out and roll out working with live data feeds. It would be interesting to work with several TMCs, for instance, that that could provide access to their live data sets as well as to their archive data sets, and see about enabling a number of concurrent analyses. Again, depending on the complexity of the use cases.
Okay. We had another question come up in the presenters chat pod that I'm about to paste into the public chat pod, and it comes from Robert Rausch. Question for planning and post-delayed analysis. He says that he sees the use of big data, but shouldn't we be focused on trying to push edge computing?
I can go on that. That's a pretty good question. I think, yes, we definitely need to emphasize on edge computing also, where you don't have to push everything to the cloud, but then you have some devices that can process the feed themselves and send very little information to the cloud. Now, the challenge here, right, with the data we're dealing with, it's not that we are sending so much information. Like every minute, you're sending a very small size data to the cloud. Okay, but over time it grows and becomes huge. That's why we need to develop these tools. But definitely, yes. Like with video data, it will be really good if we do processing on the edge and send very limited information to the cloud. I totally I agree with you.
Okay, thanks, Doc. Any thoughts on that, James?
It's a topic that has really caught attention over the past couple of years in terms of the potential for edge computing. There are a number of now low-cost detection methods that used to be prohibitively expensive before, like LiDAR, for instance, where you can get a lot of detailed information about vehicle trajectory, vehicle classifications, and certainly that brings up a lot of a question about, well, from a practicality standpoint, you don't want to send all of those LiDAR reads into a cloud like Dr. Adu-Gyamfi mentioned before. It's one thing if you've got some kind of loop detector that's on a point and it's sending little bits of data, and yeah, you in the long run you end up with a big problem with a lot of data sitting on a cloud. But what about some of the newer generation of detectors or connected vehicles themselves? That's where edge computing really has a lot of value, and there's a lot of attention to that right now, and I'm aware that that's been a topic of exploration for some of the more recent exploratory advanced research problem statements.
Okay, thanks, James. Well, we're pretty much right at our time right now. Let me check the chat pod to see if we have anything. Okay, so I want to thank Dr. Adu-Gyamfi and the University of Missouri, Columbia for your presentation today. Thank you very much. Also to James Pohl of Turner Fairbanks. I really appreciate you guys coming out and giving us an overview of these tools. I also want to thank the National Operations Center of Excellence and NELU for partnering with the Federal Highway Administration's Resource Center to bring this to the discipline. Also, I wanted to point folks that are still here to the Useful Links pod, which has links to resources within the center, National Operations Center of Excellence, as well as there is also a link to part 2, to register for part 2 of this webinar, which will be held May 5th from 1 p.m. to 2:30 p.m. Eastern Time next week. And with that, I'm going to go ahead and close it out. But again, I wanted to thank the speakers, Dr. Adu-Gyamfi and James Pohl. Great work, great exchange as expected.